On August 11, 1999, a total solar eclipse swept across Europe and Asia. If you stood in the right spot, the moon blocked the sun at the exact second astronomers said it would. In fact, we can tell you right now that on September 3, 2081, another total eclipse will darken the skies over Switzerland. We can map its path down to the meter, decades in advance. Our universe feels like a flawless, deterministic clock. We can predict the dance of the Earth and the Moon thousands of years into the future using nothing more than Isaac Newton's laws of motion. But what if I told you that this entire cosmic certainty is a fragile illusion? If you take our predictable Earth-Moon system and drop just one more celestial body into the mix, a second sun or a passing star, the clock shatters. The math breaks, the future becomes entirely, fundamentally uncomputable. This is the three-body problem, and it's the ultimate proof that the universe loves chaos. This is Elaxior, Science Visualized. To understand why three bodies break the universe, we first have to appreciate why two bodies work so beautifully. Back in 1687, Isaac Newton published the Principia, introducing his universal law of gravitation. He proved that gravitational force between two objects depend on their masses and the distance between them. When you apply this formula to just two objects like the Earth and the Sun, something magical happens. The math yields an analytical solution. That's a fancy way of saying you can plug in any time into a single, elegant equation and it will output the exact position of both objects. It doesn't matter if you want to know where Mars will be tomorrow or in 5 billion years. The math is a straight line. It's predictable because the two objects share a single center of mass locked in a permanent geometric tangle. Kepler called them ellipses, Newton called it a solved problem. Physicists felt invincible. They thought if we can solve two bodies, we can solve anything. We just add a third body, run the numbers, and map the whole universe. Of course, they were dead wrong. In physics, going from 2 to 3 isn't an incremental step, it's a leap of a cliff. When you have three objects pulling on each other simultaneously, the simplicity vanishes. Every time planet A moves, it changes the gravitational pull on star B. Because star B moved, its pull on a star C changes, and because star C moved, it alters the trajectory of planet A. It is a non-stop interconnected feedback loop. In the late 19th century, King Oscar II of Sweden offered a massive cash prize to anyone who could solve this. The brilliant mathematician Henri Poincaré took on the challenge. He tried to find a master equation with three bodies, a definitive formula just like Newton's. Instead, he found chaos. Poincaré realized that the three-body system is plagued by what we now call extreme sensitivity to initial conditions. If you run a two-body simulation and alter the planet's starting position by 1 millimeter, the future orbit barely changes. But if you alter a three-body simulation by the same millimeter, within a few dozen orbits, the entire system looks completely different. One star might get flung out into the deep void of space, while the other two collide. Hold on, you might say we have supercomputers now. Why can't we just brute force the math? Well, we can, but there's a catch. Computers don't solve the analytical equation because, as Poincaré proved, a general analytical equation doesn't exist. Instead, computers do numerical integration. Essentially, the computer looks at the three objects right now, calculates the forces, moves them forward by a tiny fraction of a second, and repeat the process over and over. It works great for weather forecasting or launching rockets, but because of chaos, those tiny rounding errors in the computer's code accumulate. Over long periods of time, the simulation inevitably drifts away from reality. To make matters worse, three-body systems love to tease us. There are actually a few special cases where three bodies form stable, predictable patterns, like the Lagrange points, where a tiny third body sits perfectly balanced between two massive ones, or the figure 8, discovered in 1993, where three equal masses chase each other perfectly along a figure 8 path. But these islands of order are incredibly rare. In the real universe, most three-body systems are unstable, unpredictable, and violent. So, why does this matter? If our solar system is stable enough to predict eclipses, why care about the math breaking? First, our solar system isn't perfectly stable, it's actually a multi body problem. The only reason it looks like a stable two body system is because of the Sun. It's so massive, completely dominates everything else, Jupiter handles the rest. But over billions of years, chaotic interactions could theoretically cause Mercury to fly out of the solar system entirely. Second, the universe is full of three-body systems. Take Alpha Centauri, our closest star system. It consists of three stars, Alpha Centauri A, B, and Proxima Centauri. If there are planets orbiting within that system, their skies wouldn't have predictable seasons. They would experience eras of scorching heat when close to the stars, followed by random centuries-long ice ages when plugged into the outer edges. Isaac Newton gave us a universe of laws, order, and predictable geometry. But Henri Poincaré showed us that right beneath the surface of that order lies a deep fundamental wildness. The three-body problem reminds us that nature cannot always be tamed by an elegant equation. Sometimes the universe refuses to be calculated. The next time you watch a solar eclipse, appreciate the clockwork. But remember, it only takes one extra star to break the clock forever. Thanks for watching. With this mind-bending physics left you questioning reality, hit that like button, subscribe, and let me know in the comments. Would you ever want to live in a 3-star solar system? See you next time.